Welcome to this explainer. Okay, I want you to take just a second and imagine shrinking down, like really shrinking down. Because right now, inside your body, inside literally every single bone, every breath you take, every beat of your heart, there is an entire hidden universe. We're going to zoom way past the cells, past your DNA, and dive down into structures so impossibly small that they honestly kind of defy human intuition. Today, we're exploring the invisible, explosive, totally dynamic forces that literally make up you, me, and, well, everything around us. Let's get into it.
So to truly wrap our heads around this atomic universe, we first have to grapple with the sheer scale of what we're actually looking at. 10,000. That's the number you need to keep locked in your head right now. The atomic structures we're exploring today are 10,000 times smaller than a single strand of human hair. I mean, to put that into perspective, it's a level of reality so microscopic that it almost feels like science fiction, but it is happening inside you at this very second.
Okay, let's dive into this, because this visual completely shatters our normal everyday perception of solid matter. If you were to take just one of those atoms and blow it up to the size of a massive, roaring football stadium, the nucleus, the absolute center of it, would be no bigger than a single glass marble sitting right there on the 50-yard line. The rest of that massive stadium, it's just electron clouds and empty space. Essentially, everything you consider solid is mostly just a vast, invisible arena. Crazy, right?
So formally speaking, what's the science that actually maps out this invisible stadium? Well, it's atomic physics. This is the precise study of the composition of the atom itself, those electrons, protons, and neutrons, and exactly how they interact with other particles and subatomic energy states. And what I find so fascinating here is that this isn't just some abstract academic theory. This is a brilliant, highly practical, real-world application of quantum mechanics.
And to connect that abstract definition right back to reality, look at these essential pillars of modern physics and technology. We're talking about the lasers cutting through industrial steel, the MRI machines that map the soft tissues of our bodies with just incredible precision, and of course the entire dawn of the nuclear age. All of these monumental human achievements, they were born entirely from understanding that tiny little marble at the center of the stadium.
All right, moving into part 1, radioactivity and the unstable nucleus.
Now, what's really interesting about this is that atoms aren't always these perfect, happy, little stable spheres. When a nucleus gets too large, this epic, invisible tug-of-war begins. On one side, you have the electrostatic force of repulsion between protons, and it's trying to aggressively tear the nucleus apart. On the other side, the nuclear force of attraction is desperately trying to hold the whole thing together. And when that force of repulsion finally overwhelms the attraction, well, the nucleus reaches a breaking point.
And when it breaks, it decays. The nucleus just violently fractures, throwing off 3 distinct types of emissions. You've got alpha particles, beta particles, and these intense, glowing waves of gamma rays. This totally chaotic, energetic fracture, that is exactly the phenomenon we call radioactivity.
But here's the thing. This chaos actually isn't random at all. It follows these really strict, unbreakable laws. You start with step 1, a large, unstable parent nucleus, like uranium. Then in step 2, it undergoes that dramatic particle emission we were just talking about. And finally, step 3, it transforms into an entirely new daughter nucleus, like thorium. What's absolutely incredible here is that the new daughter atom has completely different physical and chemical properties from its parent. It's literally the transformation of matter.
So, the crucial point to take away here is that this decay is a relentless, unstoppable clock. The rate of radioactive decay literally cannot be sped up or slowed down by heat, pressure, or, any chemical process known to humanity. It ticks exactly at its own pace. And this inescapable countdown is the fundamental secret behind radioactive materials, and really, it's the raw beating heart of nuclear power.
Okay, let's transition into part 2, nuclear energy. Fission versus fusion.
And this brilliantly illustrates a profound manipulation of those atomic laws, changing one element entirely into another just to release a literal universe of energy. But there are 2 totally different paths to get there. First, we have fission, the act of splitting a heavy nucleus into 2 lighter ones. This triggers an exponential, cascading chain reaction, which is the heavy-lifting reality powering today's nuclear plants. On the flip side, we have fusion, combining 2 light nuclei to form a heavier one, releasing even more massive amounts of energy. Fusion is this awe-inspiring, clean promise that powers the sun and the stars, and it is the holy grail that might just power the entire civilization of tomorrow.
Moving right along to part 3, the mechanics and reaction types.
Let's take a quick breather and systematically break down exactly what's happening inside those reactors. We're looking at 4 main types of reactions here. First, elastic scattering. This is where particles bounce off the nucleus just like billiard balls, meaning no kinetic energy is lost. Second, inelastic scattering. Here, energy actually is transferred, leaving the nucleus excited beyond its threshold. Third, transfer reactions, where a particle is absorbed and 1 or 2 different particles are forcefully discharged. And lastly, capture reactions. The nucleus absorbs a particle and releases these brilliant waves of gamma rays. These 4 mechanics, both the quiet and the loud ones, govern absolutely everything happening inside a reactor core.
Bringing us to part 4, the ascent. Let's talk about why this actually matters. Let's zoom back out for a second. Up from the microscopic level, through the electron shells, through the molecular bonds, back to the human body, and right out to the modern city. Why does this invisible science actually matter to us? Because it's the foundation that built the world you navigate every single day. The smartphone sitting right there in your hand, the steady stream of electricity humming in your walls, the advanced medicine that has saved countless lives, all of it, literally every single everyday miracle we completely take for granted, traces its existence back to understanding what happens inside the tiny vibrating nucleus of an atom. I really want to highlight this profound realization from our source material today. Read this with me. The universe is not made of rocks and water. It's made of invisible, dynamic, explosive interactions happening right now inside you. I mean, wow, I just love that. It totally flips our whole perspective. We aren't just solid objects passively moving through space. We are fundamentally made of these chaotic, beautifully structured microscopic forces. Which kind of leaves us with one final awe-inspiring question, doesn't it? If the universe is really built on these invisible, explosive interactions, how will we harness them next? Is it going to be boundless fusion energy, brand new frontiers in medicine? The possibilities are quite literally as limitless as the atomic structures themselves. Thank you so much for exploring this explainer with me today. Keep questioning the world around you, and I'll catch you next time.